So my name is Alec Dektor. I'm a part of the Scalable Solvers group here in the Applied Mathematics and Computational Research Division at Berkeley Lab. And today I'm talking about high-dimensional integration with low-rank tensors. So computing this number I, which is the integral of some d-dimensional function f, where d is potentially a large number, has many applications in scientific computing, such as computational finance, where you want to predict future stock prices given the history, or fluids, where you want to do uncertainty quantification of some PDE that has some random parameters, or in quantum many-body problems, where you can express many observables or other quantities of interest in terms of high-dimensional integrals. And so, of course, we have many quadrature rules, which are numerical methods that allow us to compute integrals efficiently in one dimension. And if we try to extend these quadrature rules to higher dimensions using tensor product grids, then we obtain numerical methods that have computational cost scaling exponentially fast with the number of dimensions. So for this reason, there's been a number of algorithms proposed to compute high-dimensional integrals at a lower computational cost. And each of these methods have a different way of exploring the high-dimensional space that underlies the function f. So perhaps the most well-known method is Monte Carlo, which explores this high-dimensional space through randomly sampling. And then there's methods like sparse grids, which place many points in certain regions and fewer points in other regions. And then there's these low-rank methods, which are about finding points in high-dimensional space and then interpolating the function on crosses that pass through these points. And so today, I want to talk about this perhaps lesser-known low-rank approach to computing high-dimensional integrals. I want to discuss how it works and give an example of its application. And so the first thing I want to point out is that these methods have computational costs scaling as dnr cubed, where d is the dimension of the function, n is the number of points that you use to discretize each dimension, and r is the so-called tensor rank of the approximation to f. So these algorithms scale linearly in dimension and cubic with respect to this parameter r. And so when you can approximate f with low tensor rank, then these methods are very efficient. Okay, so how does this work? Well, what we do is take the function f and use an existing algorithm, for example, a greedy algorithm, to obtain a low-rank approximation of the function f. And this low-rank approximation is a product of these objects psi, and each psi depends only on one variable, x1, x2, and so on. And these objects psi are matrices that contain one-dimensional functions. And the dimension of this matrix is r by r, where r is the parameter corresponding to the rank of the expansion. So large matrices means you have a lot of one-dimensional functions. That's an expensive method. Small rank means small matrices, not a lot of functions, and you have an efficient method. So computing this type of low-rank expansion can be done on the order of dnr squared evaluations of the function f. It's parallelizable across the dimensions d. And perhaps one drawback of the method is that it requires the domain of the function f, or your region of integration, to have a relatively simple structure. It has to be a hypercube or a Cartesian product of one-dimensional sets. So once we've computed this low-rank expansion of the function f, then we can go ahead and compute the integral relatively cheaply just by moving the integral sign through the product and using the one-dimensional quadrature rules on each of the one-dimensional functions that we have from this low-rank expansion. Okay, so let's see an example of this in practice. So here we're going to represent some observables as high-dimensional integrals. So I'm considering the single impurity Anderson model, which describes a magnetic impurity inside of a metallic bath. And using perturbation expansions, it's possible to express various quantities of interest, such as the partition function of this system, which can tell you stuff about the free energy or the total energy of this system, for example, in terms of high-dimensional integrals. It's also possible to get the Green's function in a very similar way. And the Green's function can tell us other interesting stuff about our system, for example, if it's an insulator or a conductor. And now each of these partition function and the Green's function is a series expansion, and as we go further out in the series expansion, we have higher and higher dimensional integrals that we need to compute. And what I'd like to point out about these integrals is that they're not over this hypercube, rather they're over this SK, which is a k-dimensional simplex. So it's a more complicated domain. You can think about it as a high-dimensional analog of a triangle. And this is not where we can use our tensor method. So in order to use this low rank expansion on this function f, we need to do something first. So what can we do? We can map a reference cube into the simplex using some kind of map that we can design. So here's 3 maps that map a cube to a simplex in 2 dimensions. And as we increase the number of dimensions, we have more and more possibilities of maps to choose. And once we've selected one of these maps, then we can express the integral over the simplex as an integral over the cube using a change of variables. So now we have an integral over a square or a hypercube of a new function, which now depends not only on f, but also on t. And then we have another factor coming in from the Jacobian of the transformation, this j of t of x. And now we apply the low-rank approximation algorithm to this integrand. And in fact, we can try to choose this matrix T in order to uncover low-rank structures in the function f so that the algorithm performs as well as possible. So let me describe how we can do that. So here we have a function f that has this property that it's time translation invariant. And so this property occurs, for example, in the partition function of the single impurity Anderson model. And what this means algebraically is that if we translate the arguments of the function f, we recover the same value. Okay, so how can we use this, exploit this when we try to construct our map T? Well, here's 2 possible maps T. And if we consider this algebraic property as a geometric property, what it's saying is that the function f is constant along these green lines that are uncovered by this map T2. So f is constant along these lines, and what this means for the composition function that we're going to integrate is that this composition function is a constant function of x1. And the implication of that is the rank of this f of t2 of x is going to be smaller than the rank of f of t1 of x. And so we'll get a more efficient numerical method when we apply the low-rank approximation to f of t2 of x as opposed to f of t1 of x. And in fact, when we take a greedy algorithm for approximating functions using tensor train, what we find, which is a low-rank tensor format, what we find is that the approximation with the map T1 converges significantly slower than the approximation with the map T2. And in this case, we can get about 2 orders of magnitude more accuracy out of the map T2 than we can out of the map T1 for the same rank. So what I hope you have taken away from this is that these low-rank methods are perhaps a lesser known, yet still powerful method for approximating high-dimensional functions and also computing high-dimensional integrals. And so all you need is a function f of x that has a domain that's a hypercube, and you can apply some black box algorithm to obtain a low-rank separated expansion from which you can efficiently perform computations, for example, computing integrals. And even if your function is not defined on such a simple domain, it's possible to design maps from the domain you have to this hypercube and uncover low-rank structures in the process. And in the case that you have a function f that you can have low-rank structure uncovered by a map or already has low-rank structure, then it's possible to compute integrals to very high precision with a relatively low computational effort. And with that, I thank you all for your attention.